Okay, so I'm going to discuss work done with David Kutazov a few months ago on fundamental strings and black holes. And it's not on? I have so many, I don't know which is on. Did it go? This is on.
We have two.
Yes. יכול לשים את הכל on? זה על on. It's on. Is it okay now?
לא, אני אשים ווליום.
No. Is it okay now?
כמה שיותר גבוה.
Okay. Now, remarkably, this work uses some very old works of Eliezer from 20 years ago. One involves the sigma model background description of the Goddard-Kent-Olive construction of cosset conformal field theories, works that were published in '88. And another one is the famous cigar work done by Eliezer with Shmuel Elitzur and Abraham Ferge, and even more recent works that are very directly related to what I'm going to say today. Now, clearly, like any other matter, if fundamental strings are interacting gravitationally strongly enough, they will form black holes. More explicitly, if we have a fundamental string at an energy excitation, which is much, much bigger than the string scale divided by the string coupling squared, then gravity is strong enough to form a large black hole. However, as we formally take the limit that the string coupling becomes very small, the fundamental string becomes a perturbative string, explicitly when the mass of the excited string is much, much smaller than 1 over the string coupling square, then the string is perturbative, and we can use perturbative string theory textbook to analyze such strings, although the mass can still be much, much bigger than the string mass scale. Interestingly, in the extremal case, say in 4 dimensions, it is claimed with various very strong arguments that the near horizon of a 4-dimensional extremal black hole, say, is an ADS 2 times S2, and that this fact and the parameters that describe the near horizon are completely independent on the value of the asymptotic string coupling, namely the value of the dilaton in the asymptotic regime far away from the black hole. This means, in particular, that the ADS 2 times S2 provides a dual description of the thermodynamics of perturbative fundamental string, something that was checked a few years ago. Now, an immediate question that this suggests is the following: is there a worldsheet conformal field theory background dual in an appropriate sense to perturbative fundamental strings with generic charges? By generic fundamental string charges, I mean winding n, winding W and momentum n, say on a circle, with radius r, and I will use the notation where Q is a vector in the even self-dual lattice gamma 1, comma 1. Explicitly in terms of the radius, momentum, and winding, it takes this form. So what I'm going to give today is a proposal for such an exact worldsheet conformal field theory. In particular, in the extremal case, we will thus find the exact conformal field theory background corresponding to small black holes. And moreover, we will find the exact conformal field theory corresponding to the near horizon of black holes with generic electric and magnetic charges, hence deriving properties of such dionic black holes exactly in alpha prime, both for BPS, for supersymmetric, as well as non-supersymmetric black holes. I will begin the discussion with the case where we have both electric and magnetic charges. And later in the talk, I will turn off the magnetic charges so that I will talk about fundamental strings. And I will consider first the case of a heterotic string compactified to 3 + 1 dimensions on 2 circles that I denote S1 and S1 tilde, and then the rest of the internal space is going to be a complete spectator in my talk. Okay, so suppose I start with a heterotic string on such a background, and I want to introduce magnetic charge. It's possible to add Navier-Schwarz fibranes, which wrap on the circle S1 and the 4-dimensional manifold M4. I can put, W tilde of them. The near horizon of these fibranes look like an infinite throat. The radial direction can be parameterized by a real scalar that I will call phi with a linear dilaton along it. And in Euclidean space, I will also have a compact time, and I can think about it as an infinite cylinder. This is the CHS background. So the near horizon of such W tilde Navier-Schwarz fibranes is the conformal field theory on the time, the scalar phi with the linear dilaton. There is an SU2 WZW model which correspond to the 3 angular directions of the 4 dimensions transverse to the Navier-Schwarz fibranes. And then there is the S1 times M4 on the word volume of the fibranes. We can, moreover, introduce magnetic charges corresponding to KK charges, to Kaluza-Klein charges, N tilde KK monopoles. The KK monopoles that I will introduce will be BPS with the Navier-Schwarz fibranes. And again, it is known in conformal field theory what the description of these magnetic objects in the exact CFT of the near horizon of the fibranes. Due to works of Giddings, Polchinski, Strominger, and Kutasov, Larsen, and Lee, the conformal field theory changes by a purely left-handed asymmetric orbifold of SU2 by the Z N tilde, where N tilde is the number of KK monopoles. Now, to this system, which is supersymmetric, I want to add some energy excitation N. And in all my discussion, I fix the string coupling to be a very small number, say. L string can be taken to be 1 if I do not mention it explicitly. So I consider now energy excitations which are well below 1 over G string squared. In that case, due to work of Maldacena and Strominger from 10 years ago, it is known that the effect of such an energy excitation is to turn the infinite throat in the linear dilaton direction and the time direction into a 2-dimensional black hole, which by itself turns out to be an SL2 moded by 1 exact conformal field theory. Altogether, what we obtain after we consider the near horizon of W tilde Navier-Schwarz fibrils and N tilde KK monopoles, together with an excitation energy M, is a near extremal system whose near horizon is an exact CFT. The conformal field theory on SL2 modeled by U1 at level K times a circle S1 times an asymmetric orbifold of an SU2 level K conformal field theory times the extra internal space. The level K of SL2 and SU2 is related to the magnetic charges N tilde and W tilde in this way. And the value of the string coupling at the horizon of the two-dimensional black hole, namely Euclidean space at the tip of the cigar, behaves up to a finite number that depends on K, like 1 over the mass of the black hole. Now, to this system, I want to add now fundamental string charge, namely momentum N and winding W on S1. And it is straightforward to do it. In order to add momentum on the circle, all we have to do is to boost along the circle. And the amount of the boost produces the amount of momentum along it. Then we can perform a T-duality along the circle in order to turn this momentum into winding. And then we boost again to turn on momentum again, and we can obtain any momentum and winding on the circle. The interesting thing is that even after doing this procedure, we still land on an exact conformal field theory background. The sigma model background that we obtain after this procedure turns the direct product of the SL2 mod U1 conformal field theory times S1 into a different quotient of SL2 times U1. It's still a quotient by a U1, but now the U1, instead of acting just on SL2, acts on the Cartan subalgebra in SL2 as well as the extra U1, and the relative angle, alpha L, by which it acts on the left-handed U1, and the relative angle alpha right, by which it acts on the right-handed U1, determine the charge-to-mass ratio of the solution. So in that way, the correspondence would be that after Kaluza-Klein reduction of this three-dimensional sigma model to 2 dimensions, what one obtains is a 2-dimensional black hole with 2 charges that I call Q left and Q right. And Q left and Q right are related to the winding and momentum of the fundamental string in this way. Now, given this black hole, one can compute its entropy, for instance. One can compute anything because it's an exact conformal field theory. In particular, one can compute the entropy of this black hole. So this was done as well in work that I mentioned at the beginning, where Eliezer is involved as well, and this is the answer. So there are 4 charges involved here: the winding and momentum of the fundamental string Q left and Q right, the magnetic charges N tilde and W tilde, which are hidden in K, and the result for the entropy is written here. This result, I should emphasize, is exact in alpha prime. Of course, it receives corrections in the string coupling. And everything that I say today is exact in alpha prime, but is only leading order in the string coupling. And what I want to do next is consider some special cases of interest, one by one. The first one is the extremal case. Very briefly, I will say something also about the very extremal case. And then I will discuss perhaps the most intriguing one, the one where we have no magnetic charges at all, namely the case of small black holes. The extremal case first. There are two cases in the heterotic string. One is the case when the mass is equal to the right-handed sector I take to be the fermionic sector of the heterotic string, and the left-handed sector is the bosonic one. When the mass is equal to the right-handed charge, these are the Volcker-Harvey states. They are supersymmetric. Q left can be generic. Another case, which is extremal, is the case where m squared is equal to q left squared minus 1, while q right is arbitrary. This is extremal but not supersymmetric in the heterotic string. Both cases amount to particular gauging of SL2 times U1, where the U1 acts only on the left side of the SL2 in one of the cases, or only on the right-hand side of the SL2 in the other case. And one can show that upon reduction to 2 dimensions, the background obtained in this case is an ADS2 times a circle. Similarly, the reduction of SU2 moded by the purely left-handed asymmetric orbifold is an S2 times S1 tilde. But it's better than that. The radius of ADS2 and of the two spheres are determined in terms of the charges. Explicitly, the radius is the square root of k up to L string over 2. K, I remind you, is n tilde W tilde plus 2. Also, the radii of S1 and S1 tilde are fixed in terms of the charges. They are given by the square root of the ratio of the electric charges for one circle and the ratio of the magnetic charges for the others. There are also gauge fields with constant field strength on the ADS2 and S2. Again, the field strength is obviously proportional to the charges, and there is a constant dilaton giving rise to a string coupling, which is determined in terms of the charges to take this form. The entropy that I wrote to you before in this particular case is different in the supersymmetric and non-supersymmetric case. In the supersymmetric case, it's this form. In the non-supersymmetric case, it's what's reading in that line below. You can see that to leading order in alpha prime, it behaves like the square root of the product of the 4 charges. This is the famous result that everybody knows for the entropy of such black holes with 4 charges. But here, this is an exact result in alpha prime. So the plus 4 here and the plus 2 here know the difference of a factor of 2 between the supersymmetric and non-supersymmetric cases is a consequence of the fact that we study an exact conformal field theory, and hence we produce this result exactly in alpha prime. Now, there are many works on this topic, so this is a good point, of course, to compare these results with previous results. So this is what I want to do next. It's not done in an historical way. So first, there were some works of Sen in the last couple of years where Sen did the following thing. He started with the leading order low energy effective action of heterotic strings and added to it a single term, which was e to the minus twice the dilaton times r squared written in the Gauss-Bonnet scheme, and that's it. By no way this is a low energy effective theory of string theory. It stops at leading order correction in alpha prime, even if he set the coefficient lambda to be that of the heterotic string, while the heterotic string will have many higher order corrections. Even to this order in alpha prime, I mean, the heterotic string has many other fields and many, many other terms in the effective action even at this level. Well, but he studied this theory, studied it for good reason, because with this effective action, he could find an exact solution, which is an ADS2 times S2. So he plugged in an ansatz of an ADS2 times S2 into the action. When lambda equal to 0, the solution is singular. But when lambda not equal to 0 is turned on, the ADS2 times S2 solution becomes non-singular, and it's an exact solution to the equations of motion of this lambda r squared theory. And remarkably, the solution that Sen obtained for this action in this way is precisely this one. And by applying the Wald formula to his solution, note that Sen in his formulation only has the near horizon geometry of the black hole. So he must apply the Wald formula, the generalization of the Bekenstein formula, to higher derivative gravity in order to find the entropy. And he finds that the entropy in any case is S sub z. So he finds the right result in 50% of the cases. If we consider the supersymmetric case, it's the correct result. If it wasn't the supersymmetric case, it's the wrong result. But it didn't have to be the correct result in both cases, because nowhere did he do an effective action of string theory. Well, I think that in the supersymmetric case, one could claim that some non-renormalization theorems could be used to prove that although a priori there was no reason that he will get the right result, he actually should have gotten the right result. Now, second set of works that go a long time ago by DeWitt and various other people. I think that almost all these works include Lopez, Cardoso, and Haupt. The initial one probably, and maybe Bernard will correct me if I'm wrong, include also Berndt and Dieter Lust. These theories, these works involve supergravity in 4 dimensions. And again, like the previous stories that I told you, the action that they use is not the low energy effective action of the heterotic string. It involves the Weyl multiplet and an R squared term in the Weyl scheme, plus terms that are required by supersymmetry. And by using supersymmetry, again, one can find via the attractor mechanism an exact ADS2 times S2 solution to the equations of motion, and applying the Wald formula to this solution, one obtained this result. The same result as the one that I wrote here in the supersymmetric case. For extremal non-BPS cases, there were further works of Krauss and Larsen and Sahu and Sen. Krauss and Larsen, assuming that the solution is locally in ADS3 and using some anomaly arguments, obtained these results as well. Sahu and Sen just took the low energy effective action of the heterotic string to leading order correction in alpha prime and found the linear solution, namely if one would expand these results in 1 over n tilde w tilde, this would be an expansion in alpha prime, and the leading order correction in alpha prime that they found agree with these exact results, both, of course, in the supersymmetric and the non-supersymmetric case. Sure.
Do you think solutions only exist because of the R squared
I'm not aware of people knowing to find solutions to other actions that involve higher derivatives in them.
But don't you have all four charges? I thought just under Einstein gravity, the four charges
To leading order in alpha prime, the solution is singular unless you have four charges, these four charges. But once you add r squared, once you add r squared, this solution this become regular.
It's just that you have formula for the all four charges, but then you switch to discussing just the two charges. Okay.
At the moment, I didn't switch to discussing only the two charges. This will be, I'm in exam. Well, I'm sorry? Okay. Let me put back things in order. There are three examples that I'm in one. I'm discussing extremal cases. They can have four charges if you wish. It's only in three that I will turn on two charges. I will turn off two charges. I didn't do it yet.
Once you turn on the R-squared term, what does it prevent?
I'm sorry, I can't hear you.
Is it known why the high order term?
I think they may contribute. Generically, they should contribute. Perhaps in the supersymmetric case, there are some non-normalization that tell you that the contribution vanishes, but a priori, of course, they contribute. It so happens, answer analysis, they don't. At least they don't contribute to the entropy. And they don't affect the geometry in the nearby, but a priori, you couldn't know it. I'm just describing what was done in the literature. A priori, it didn't have to give you the exact result. In the supersymmetric case, it so happens that it does give the exact result. In the non-supersymmetric case, it doesn't. Now the second case is the very extremal one. There M is both equal to the right-handed and the left-handed charge, so we can think about it as the case where we only have fundamental string winding W times on the circle, or if you wish, W fundamental string. And in that case, the quotient of SL2 times U1 by 1, the gauge U1 does not act at all on SL2. So one is left with string theory on SL2 or string theory on ADS3 at level K with Navier-Schwarz charges only. So this is the model that I considered with David and Ati some time ago. And for the particular case that involve also these magnetic charges, it was done in the work of David with Larsen and Lee. And okay, I won't say anything about that except that one obtains what one expects to get in this case for this model. So now we'll turn perhaps to the more interesting case of small black holes, namely the case that describe perturbative fundamental strings. Why perturbative? Perturbative because all over what I did, I consider the near horizon limit of the fibrils. So equivalently, if you wish, I consider the limit where G string is very, very small. So now that I turn on the magnetic charges, I still stay in the limit where the string coupling is very, very small. And if you remember, the energy excitation that I added was much smaller than 1 over G string square. So this is the regime of perturbative fundamental strings. So the moment I turn off the magnetic charges, I'm in this regime of perturbative fundamental strings. Well, turning off the magnetic charges, now that I have the exact CFT at hand, maybe I will flash it again. Okay, so this is the exact CFT. So I have it, here it is. So I want to turn off the magnetic charge. Okay, I'll set the magnetic charge to 0 and see. If the CFT makes sense, I go ahead. It does. Setting n tilde equal to 0, k is equal to 2. SL2 level 2 mod U1 makes perfect sense. SU2 level 2 makes perfect sense as well. Actually, its bosonic part is trivial, so it makes sense in a very simple way. So this is what I'm going to do. I turn the magnetic charge to 0 and go ahead and take seriously the conformal field theory that I obtain and study its properties. So this is the conformal field theory that, no, it's not this one. It's the next slide. It's this one. So the sigma model background is that of an SL2 times U1 modeled by U1. It's the three-dimensional sigma model. There is also the four-dimensional space. And then there are also free fermions involved. Here I wrote only three of them, psi1 bar, psi2 bar, and psi3 bar, because these are the three right-handed fermions that form the SU2 level 2. It's a tricky way. It's an explicit way to represent the SU2 level 2 that is left here. And I wrote for you previously the entropy in the general case, and all what I have to do is when I set the magnetic charge to 0 is to plug in n tilde equal to 0 in that formula, and what I should better get, if everything is consistent, is the entropy of free fundamental strings. And indeed, this is the case. The black hole entropy in that case is precisely the entropy of free fundamental string. It should be emphasized that there are two free parameters here. It's precise for any mass and any winding and momentum of the fundamental string. So this leads immediately to the proposal. And I talked about the theoretic string so far, but now that I present the proposal, I will do it in order to add more flavor to the story in the type 2 case. So it immediately leads one to propose that the SL2 level 2 times U1 modeled by U1 times any internal 5-dimensional space type 2 string theory, that this worldsheet background is the near horizon conformal field theory of perturbative fundamental strings, namely of fundamental string with mass which is much, much smaller than 1 over G string squared, with winding and momentum N and W, where the winding and momentum are determined by the way the gauge D1 acts. And in particular, in the case when I set also the electric charges to 0, so that I consider just 4-dimensional Schwarzschild black holes, in the limit when the string coupling goes to 0, when I go to the perturbative string regime, the claim would be that the near horizon of such 4-dimensional Schwarzschild black hole will develop a semi-infinite throat of the SL2 mod U1 cigar at level 2, with the string coupling at the horizon behaving like 1 over the mass of the Schwarzschild black hole. Well, I can say more, but maybe it's a good point to stop and take questions if there are any.
The fact that G at the horizon goes like 1 over n, is this not a cause of worry that the loop function will break that?
No. Okay, so in the regime where the mass is much bigger than the string mass field, this is a small number, and loop corrections are small. And in fact, it's a doable exercise, at least to do the one loop correction. And the one loop correction should provide a correction to the entropy, for instance. So this entropy is correct for large enough mass. And one loop computations for string theory on the SL2 mod U1 cigar will provide corrections in 1 over m to this equation, to this formula for the entropy. it's safe until you go to masses that are, that are closer to the string scale. There, the string coupling at the tip of the cigar is strong, but this is good because the number of states is finite for such small energy levels, and you expect large fluctuation of the geometry. And large string coupling for small mass is the thing that you would expect intuitively, and indeed this is what you get.
Because I remember when you were computing these loop corrections to, or massive normalization corrections to fundamental string mass, you get effects which go like g squared n. If that is of order 1, you will get worried. In other words, g Newton times the mass of the string was a relevant parameter, I thought.
At which regime?
When you look at the fundamental string and try to compute the one loop corrections to its mass normalization, that typically depends g squared n divided by some size.
But if
it's just a normal, it's very intuitive self-energy, binding energy.
But if g squared is much, much smaller than 1, then this
No,
is a small.
g squared times n, you get.
It's much smaller than n.
No, g squared, sorry, I was wrong. G squared n squared. You check. It's g Newton n squared. Because each piece of the string interacts with each other piece of the string. So it was, sorry, g Newton n squared, and so percentage-wise, you have to keep g squared n small. I mean, this is where the string entropy and the black hole entropy match. Is when g squared n is 1.
Yes, but okay. We consider a regime that is.
Now you take m squared much smaller than 1 over t squared, so that looks fine. But then it's not near the horizon. Yeah, this is the picture.
No, I know. I hope that I have a picture that could answer any question. Yeah, so you're talking about this regime.
Yes.
The regime of the correspondence, yourself, Lenny, Robertson, Kuczynski. I was discussing this regime, which is very far away from the correspondence regime.
Yes, I understand that. But I thought that the fact that g at the horizon becomes of order g squared at the horizon becomes of order n, I thought it could be a threat. But
It's at the horizon of the 2D black hole. Not to be confused with the... Okay, so...
Okay, maybe I'm confused.
It's okay, I have a picture for that as well. No, I could talk more.
I'm sure
but,
I understand.
So there is a... Okay, so suppose you would study just a 4-dimensional solution. Take a string to be 1 and g squared be very small. What do you find? And you find a Schwarzschild solution. To leading order in alpha prime, you find a Schwarzschild solution. The Schwarzschild solution has constant dilaton, and the value of e to the phi, which I choose to write here as a function of the distance from the horizon. The horizon is a g squared n, the horizon of Schwarzschild. So I pretend as if it is Schwarzschild, no matter what m is. Certainly, if g squared m is large, this is just large Schwarzschild black hole, and alpha prime corrections are very small. Then the value of e to the phi is g squared. It's a constant. Now, I even wrote here Schwarzschild metric below. Now, what the consequence of the proposal that I gave tells you that as you go towards the origin, if g squared n is much, much smaller than 1, then by the time you go to a distance 1, a string length scale, from the origin, which from this would be singularity of the Schwarzschild black hole, something dramatic is happening. The space starts to generate a throat. And as you go down deep the throat decouples from the two sphere, and by the time you go deep enough into towards the origin of, towards the singularity, you see this infinite throat. It's not only that I have words for it, I also told to you in the limit that g squared goes to 0, I told you what the exact CFT of this throat is, and it's the cigar solution that Shmuel Avraham Eliezer wrote at the time, as I said, which I wrote here. And for that solution, e to the 2 phi is the other line that I draw here. And the two lines, the matching is precisely at the point, is roughly at the point where the string couplings are the same. And this indeed is happening when R is of the order of the string scale. And from that point, I don't trust Schwarzschild at all anymore. And the proposal that I presented here tells you that an appropriate description now is the exact CFT of the SL2 module 1.
Okay. More questions? If not, it's time to speak.